introduction, we're going to look at all the stuff we've done here on factoring. So today's the day where we look at, why is that useful? What do we do with it? So we're going to solve polynomial equations, and at the end we'll look at just a few applications of polynomial equations. But mostly we're solving polynomial equations. So quick review, and this is right out of the textbook. Just a kind of a review of factoring polynomials, right? What do we do when we're factoring polynomials? Step one, we always want to see if we can factor out a GCF every time we try to do that. And then from then on out, it's just a matter of determining which strategy are we using based on the number of terms. If there's two terms, then we only have three patterns that work, right? The difference of squares, or the sum or difference of cubes patterns. Remember, the sum of squares patterns is a non-pattern. That's the one that doesn't factor. If there are three terms, this could all be summarized by just factoring trinomials, right? And that was all reviewed. Remember, we looked at on the factoring trinomials, if we've got trinomials where a is not equal to 1, remember what we did there. You guys should be, I showed you how to do, reminded you how to do slip and slide, but I really would like you guys to do grouping instead, right? Because grouping is a way better way to do it. At first, it might seem a little different and trickier, but it's not. You do the same steps in grouping, you do the same magic numbers that you would do in slip and slide, and that's the only tough part anyway, right? Is finding the magic numbers. And then finally, if there's 4 terms, we factor by grouping. And then finally, when we're all done factoring, we just want to check and make sure that none of the factors could be taken any further. Look at each individual factor and ask yourself, could it be broken down further? The only way it potentially could have to be broken down further would be if you had somehow not factored out the right GCF, or you forgot to factor out the GCF, or potentially if you had used a substitution in there. It's possible that when you use the substitution, when you apply the substitution, you may be able to factor more out, okay? So let's get rid, if you got earbuds and all that stuff, get rid of those, please. We got to really focus today. We got lots to do. So polynomial equations, what are they? Well, they're just equations that involve polynomials, that's it. Equations that either set two polynomials equal to each other, or it might even start off in standard form. Whether it does or doesn't, we always want to put the polynomial into standard form. That's our first step. What's that mean? Well, standard form for a polynomial equation is just where you have everything on one side equal to 0. That's always what standard form means for an equation, set equal to 0. And then quick reminder, a lot of times we end up with quadratic equations, which are easier to solve, and we'll focus more on solving quadratic equations with some other techniques later. And some of you already know about, like you guys already know about like quadratic formula, for example, right? But there's some other stuff we can do. That comes up later, though. Okay, so what is our strategy? Well, once we get the polynomial into standard form where it's set equal to 0, our goal then is to factor whatever's left on the other side. We get some polynomial equal to 0. And we want to factor the polynomial and then apply the zero product property, a lot of times it's called the zero product property or the zero factor property. It means the same thing. We've probably called it this in the past. Zero product property. Our textbook calls it the zero factor property. Same thing though. We know that, and we looked at this earlier, right? A product of factors can only equal 0 when you multiply by 0. So for example, if I've got the factors a times b equals 0, well then my solutions would either be a equals 0 or b equals 0. It's the only way we can multiply numbers and get 0. Okay, so then let's look at this as an example. This one's already factored for us. So what am I going to do to find the solutions? Yeah, I've got it factored. I apply the zero factor property. Right? And we know that either the first factor equals 0 or the second factor equals 0. You probably don't even have to write this step down. You can just jump right to the answer. Right? We know that either x equals -7 or x equals 2. And then whenever you're solving equations, especially on a test, you should always just check your solutions, right? Make sure they work. If I plug -7 in, I mean, obviously that's going to work because I'm going to get -7 plus 7 is 0. 0 times anything is 0. Check 2. Well, that's going to give me some number times 2 minus 2 is 0. So it works. Okay. Try another one. How about one like this? So solving polynomial equations by factoring. Step 1, write the equation in standard form. Okay. Do I have to do anything here?
No.
Done. Already done. Okay, so it's in standard form. Step 2, factor the polynomial completely. Okay, well there's how it factors. Let's remind ourselves how we do that real quick. How about? So I've got to factor the left side. Just quick review. 2x squared minus 5x minus 88. How am I going to factor that? What's my strategy there?
You have to wait. Oh, okay.
So 3 terms.
Yeah, just put x equals 8, right? Oh no, up there, top right. Wait, which one are you talking about? I'm confused.
This guy, right?
So
Because
2 times
this is how it factors, but
okay.
but I just gave it to you. Let's do the work and actually factor it. Let's remind ourselves how to actually factor that. How am I going to factor that trinomial?
You start at 2 times 88.
Okay, so I got to find magic numbers. Good. So my magic numbers, m times n, have to equal 2 times -88, so -176. And what do they add to? -5. So what's our best strategy for finding those numbers? Do we want to find pairs of numbers that multiply to -176? Or do we want to, and then, pick the ones that add to -5, or do we want to find pairs of numbers that add to -5 and then fish out the one pair that multiplies correctly if it exists?
Add.
Yeah, good. Because they multiply to a negative, it's easier to just find a list of numbers that add to -5 and see if we can pick one that multiplies to -176, right? So we build this kind of a table. All right, so which is going to be bigger, the negative or the positive? The negative, and it's 5 bigger. So the first one we could even possibly try would just be -6 and 1, which is obviously way too small. So I have to go way down the list. So throw something out, just arbitrarily.
Yeah,
Like-
try with 16 and 11.
Try which one, 16?
And 11.
Okay. So -16 and +11, and what do you know? That's it.
Ooh,
Wow.
Okay.
Good guesses.
-16, +11. So that's how. Now, what do I do with that, with those magic numbers? What am I doing with them? Why did I find them? Factor by grouping. I'm going to split the middle term so I can get 4 factors and factor by grouping. Which one do I want to do? I mean, not that it matters, but which one it would be slightly easier to group first? Which one should be? Yeah, the negative one, right? So we get the plus between the 2 groups. Minor deal, but it's, those things add up, so it makes it a little bit easier. So -5x is going to split into -16x plus 11x. Okay, so we group. What do I factor out of the first group? 2x, okay. Leaving behind x minus 8, okay. Do we know, is there a chance factoring by grouping is not going to work?
Wait, how did it not work?
If we found
If you have
the
numbers,
numbers.
they'll work, right?
You're right. If I find magic numbers, it's guaranteed to work every time. So we know it's going to work. And then second group is going to factor into what?
So we'll take out 11.
Take out an 11, good. Because remember, we have to have a common binomial factor, right? The leftover binomial has to be the same. So then that's giving us our answer, isn't it? That's giving us that gives us our, if I factor out the x minus 8, we're left with our 2x plus 11, right? I guess I got my numbers back, or my colors backwards. Did you get the idea? Okay, how are we doing? Give me 1 to 5 on that. Does that all make sense? We're getting there on the factoring trinomials. Okay. All right, so next step was we factor the polynomial, which we did. Now what? Yeah, set to 0. Apply the 0 factor property, right? So I set each equal to 0. And then what? Well, solve, I guess, right? Solve each equation. So we get 2 results, x equals negative 11 halves, or x equals 8. And then finally, on a test, what would you do? Check your solutions. Yeah, just plug them back in, right? Now remember, on the test, you're not going to have access to Desmos graphing, but you'll have access to Desmos Scientific. And you guys remember how easy it is with Desmos Scientific. I could just say, say f of x equals that whole thing, right? And then substitute and see if I get 0 on the left side when I do f of negative 11 halves. Remember that trick? You define the function, then you can evaluate it. I could just plug both of those in and just verify. Then I get 0 on the left side, and it saves a little time. You'll have access to that technology to do that. Okay. Same kind of thing. Okay, what about this one? What do I have to do first? Or is it, like you talked to me, or where do I start on this one? Okay, good, distribute to 4x. And why am I doing that?
Order of operations. So it's in standard form.
I gotta put it in standard form. How come it's not in standard form right now? Because it's not equal to 0. Yeah, right. So I've got to get everything on the left side, and I've got to write it as a polynomial on the left side. So I've got to distribute a bunch of things, right? I've got to distribute the 4x. Then what? Subtract the 5, and now I'm good, right? So I've got it in standard form. Okay, now what do I do?
Yeah, you do that.
Okay, factor it. And I try to do a GCF, but can I? Is there a GCF? No GCF. Okay, so we've got to, let's go do our factoring up here. How about? Okay, so what are we going to do here then?
32 times 5.
32 times 5, so I've got to find my magic numbers. M times n is going to equal negative 160. And what's it going to add to? 32. Okay. So the positive one has to be 32 bigger. Can you find any?
I think it's 36.
Oh, 36. Whoops. Yep, you're right.
I'm just kidding. And then the order of operations.
Okay, can you find numbers that multiply to negative 160 and add to 36? 40 and 4.
Wow.
Right, everybody see that? What are the signs going to be?
40 is positive, negative.
Right, 40 and negative. Yeah, you guys said that. 40 and negative. Yeah. Okay, so that's how that factors. So what are we going to do then? Split the middle term. Let's do the negative one first. So minus 4x plus 40x. So there's our plus sign in the middle. What do we factor out of the first group?
4x.
Leaving behind 8x minus 1. Good. And what's that give us for the second one then? 5 times 8x minus 1. Okay, so what's this factor into then?
8x minus 1 times 4x plus 5.
There you go. Okay.
Oops.
I don't know what I just did. Wasn't what I wanted to do.
You got no options.
There we go. Okay. 8x minus 1 times 4x plus 5. That's what you told me. And so now it's easy, right? We just set those, and really we can just do that in our head. If we set 8x minus 1 equal to 0, what's the solution going to be? I mean, just think about this visually. If that's equal to 0, I'm always going to just add or subtract something to the other side, which ends up where in my final answer? I'm going to get a fraction probably, right?
Yeah.
So the number that I'm pushing to the other side, when I set the blue factor equal to 0, what's going to be in the numerator of my answer? 1. Yeah, because I have to add 1 to the other side. That's the numerator. And then whatever the coefficient is, I have to divide by that. So that's the denominator, right? So I get positive 1/8 or negative 5/4. There you go. I don't know what's going on there. Something good. There. Okay. So positive 1/8, negative 5/4. Okay, I guess that's it. We solve it and then we just check, right? And then we're good. Okay, plug those back in. Okay, what about one like this? Just what would our process be here? A lot going on. What do I have to do? Standard form. So that's I can use regular order of operations, regular PEMDAS, top to bottom, simplifying. So I distribute the 3, right? Distribute the 3, distribute the negative 6. Then I would just combine like terms. I'm going to add the 6x squared over here. I'm going to add the 12x over to this side. Okay. Make sense?
Yeah.
Subtract the 13. And over here, I've really got 17, don't I? So 17 minus 13 gives me my 4. Okay. And then I would factor, and we've gone through that several times. I would just factor by grouping again. Can we think what the numbers would be here?
6 and 6.
Yeah, I'm going to get 6 and 6, right? So then I'm going to factor out. See if you can do this in your head. So if that's 6x plus 6x, I'd factor out a, what, 3x, right? I guess let's write that in there. Let's write that next one. So we get 9x squared plus 6x plus 6x plus 4. So we could factor out a 3x, right? Leaving us with 3x plus 2. And then I got a 3x plus 2 times a 3. So does everybody see we're just going to end up getting that? And we would, right? If we just go through that process. Okay, so then what are our solutions? Negative 2/3, and then same thing for both, right? So I'm going to get one solution in this case, negative 2/3, and that's it. Negative 2/3 and negative 2/3, we'd check them and they'd work. Check it and it would work. Okay. What about this one? Standard form, so what do I have to do? Subtract 16x, good. Now what?
I don't think
GCF, yeah, so what's
Ooh,
x, all right. So we can factor out an x. Now what? What do we do with this guy? Difference is squares, so how does that factor?
4. X minus 4 can be just 2, right?
Okay, but if it's 16 is 4 squared. You guys were correct on that, right? We think of that as x squared minus 4 squared. So what does my pattern tell me then? What's that factor into?
X plus 4, X minus.
X plus 4, x minus 4, right? That's my difference of squares pattern. A squared minus b squared equals a minus b times a plus b in no particular order, right? So we get that, and now we're done. What are my 3 solutions? 0, right? I set that factor equal to 0, and I just get x equals 0. Negative 4, positive 4. Okay, and then of course we would just check those and they would work. Okay. All right, so now an application, right? So what about something like this? The height, age, and feet of a golf ball after t seconds is given by this function. Height h equals negative 16t squared plus 96t. Find how long it takes the golf ball to return to the ground. Okay, that doesn't sound like math. What do we have to do here? Stopwatch. I mean, what do we do here? I mean, I guess the first step is we just have to figure out what's going on. So read and reread the problem. Okay, translate. Well, what does that mean? I mean, what is this part? How do we turn this into something mathematical? Find how long it takes the golf ball to return to the ground. What's significant about the ground?
0.
Height is 0, right? Exactly. So that's where.
It's 0.
So yeah, so we're just going to set h equal to 0 here. That's kind of the trick, right?
And you can find a GCF.
Good. And so now we're going to solve that equation, and that's a pretty easy one to solve. Good. We could factor out a GCF.
16t.
So we could take out a negative 16t. Good. We want to remember we always factor out if the leading term is negative, we factor out a negative GCF. So we get negative 16t times t minus 6, and that's pretty simple. Negative 16t equals 0 when t equals 0, right? Negative 16t equals 0 when t is 0. T minus 6 equals 0 when t is 6. So we interpret that then. What does that mean? The golf ball, 0 seconds or 6 seconds? Yeah, which is the one we're probably looking for here? 6 seconds. That first one actually makes sense though. T equals 0 is a legitimate solution. It's just not the one we're looking for. What's going on at 0 seconds? Okay, that's right when you're making contact with the ball. So it is on the ground at that time, right? We just want to know after you hit it though. So we're picking the t minus, or the t equals 6. Okay. All right, and then we could check it by plugging 6 back in, and yeah, it works. Okay, how about this one? Same kind of thing. So here's an application. The product of 2 consecutive positive integers is 132. Find the 2 integers. And well, first step, read through the problem. Right? Does this make sense? So this is one where if we're trying to come up with 2 consecutive integers, we want to assign variables to those. So obviously we got to let x equal something. Well, x would equal the first unknown number. If x is the first one, if they're 2 consecutive integers, then doesn't it make sense that the next one's got to be 1 bigger than that? So our 2 numbers would be x and x plus 1. How are we able to translate that into a math problem then? What would we get?
2x plus 1.
Wait. Okay, good. X times x plus 1. X times x plus 1 is equal to 132, right? Okay. Product of 2 consecutive integers, that's my x times my x plus 1. If I'm going to solve this thing, what would I do? Distribute, so I'm going to get x squared plus x minus the 132. So I get that. Now what? Oops, I get that. Subtract the 132, I get that. And this is a pretty easy one, right? It's a basic trinomial. Can we find magic numbers that multiply to negative 132 and add to 1?
11 and 12.
Which one's negative? 11, yeah. So we get x plus 12 times x minus 11. So what are my solutions? negative 12 and positive 11. Okay, so how do we interpret that? What were we looking for? Positive integers. Okay, so tell me about what am I going to do with those solutions then? Okay, the positive part, like think of it this way, when we're trying to set this up, we've got to translate, we're going to ask the math gods for the answer, but we're going to do that through some equation, through algebra, right? So we're going to translate this into an equation. But in this equation right here, is there anything specific about this that is really saying x has to be positive? There's not, is there? We just know that we said x is the first positive integer and x plus 1 is the second. But in this equation, I mean, there's nothing that specifically mandates that x has to be positive. We've just created an algebra equation that we're going to solve, right? A quadratic equation. So we solve that, and it turns out that that math equation has two solutions, either x equals negative 12 or x equals 11. Which one of those are we interested in? 11, because we're only interested in the positive solution, right? But really, there are two ways we could multiply numbers and get 132. I could multiply two negatives or two positives, right? So the other solution is just the math god's way of telling us, okay, this is the other solution, but we've got to pick out the one that meets our needs, which is the positive one, right? So we're going to pick the 11, and what would the other number be then? 12, yeah. X is 11, so x plus 1 is 12. Okay, so mathematically, we sometimes get more solutions than we need, right? When we're doing an application, we always want to make sure that we're going to pick the mathematical solutions that fit our situation. This stuff comes up a lot, like when you deal with geometry questions. You have some applied situation where you're dealing with like triangles or something. The lengths of the sides of any shape could only ever be positive, right? Length is always a positive thing. So oftentimes when we solve these equations to find the lengths of the sides of some shape, anytime we get a negative answer, we've got to discard that because that doesn't make geometric shape or geometric sense. It makes sense mathematically in the equation maybe, but those are solutions that don't really apply to the geometry situation. Okay, speaking of geometry, so quick review, we know Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared, right? So typically we just say a squared plus b squared equals c squared. You guys all know that. So what about one like this? Find the length of the shorter leg of a right triangle if the longer leg is 10 miles more than the shorter leg. Okay. The hypotenuse is 10 miles less than twice the shorter leg. Okay, so first we got to read and reread the problem. Got it. So now what are we gonna do here?
X is shorter.
Okay, the shorter leg is going to be x. How come the shorter leg is the one that's going to be x?
That's what it's saying.
Okay, that's good because that's the one that's referred to, right? That's the one we know nothing about that we're comparing the other things to, right? We know that the longer leg, we know something about it, is 10 miles more than the shorter leg, which we know nothing about. We know the hypotenuse is 10 miles less than twice the shorter leg, so we know something about that, but it's in terms, again, of the shorter leg about which we know nothing, right? So the shorter leg we will call x. Good. So then what does that mean the length of the longer leg is?
X plus 10.
X plus 10. Okay, and what does that mean the hypotenuse is?
2x minus 10.
2x minus 10. Good. Okay, so there's our triangle. We've labeled everything we need to. Now what do? How do we translate this into a math problem?
2x minus 10 over x plus 10.
Well, no, okay, so keep in mind, anytime you see a right triangle, and we know we're relating the side lengths of a right triangle, what are we always going back to? Pythagorean theorem. So what's Pythagorean theorem telling us then?
X squared
plus
x plus 10 squared.
Quantity squared equals
2x plus minus 10
quantity squared. There you go. Okay, good. Okay. And now we've got an equation. And so we can flip into algebra mode. We've looked at the application. We figured out how to translate the application into a math equation. Now we get to just forget about the application for a while and just do some math. Just get to work on the algebra. So to solve this, what would we obviously do here? So, okay, first I've got to, just by distribute, what do you mean here? Multiply that out, right?
Yeah.
Okay, that word we use in math for that, whenever we take some quantity to a power, we call that expanding. When we're going to expand that out to a big expression, right? When we take that binomial and we square it, and we take that binomial and square it, and we have patterns for that. What's the pattern for this one? What's the pattern for this guy right there? A Okay, you're doing what pattern though? You're doing a plus b squared pattern, right? I guess I wasn't clear on that. And what is the answer to that? A squared
Plus 2ab plus b squared.
plus b squared, good. And if we do this, what's the pattern there going to be? A minus b squared, which is really the same pattern, but what's that give us? A squared.
Minus 2ab plus b squared.
Good. So those are the patterns we're using. Okay, and that's going to give us, everybody see, this is what we're getting. That is giving us that, right? And this expression, if I expand it out, gives me that. Okay. And now I'm just going to push everything over to one side. Which side should I push everything to here? I don't know what they did, but what would be smarter?
I guess
Right side, how come? It's a little bit better to probably push everything to the right side because it gives us positive leading coefficient, yeah. Okay. And yeah, they did that. Okay. So push everything to the right side and it's equal to 0, and then we just flip-flop. So the variables are on the left. And then we factor out GCF, set them equal to 0, and we get it. So what, now let's interpret. Because we're out of math mode now. We were in algebra mode, we solved the equation, we got our mathematical solutions, but now we have to interpret. Talk to me about those solutions, x equals 0 or x equals 30. What did you say, Brandon? 30, yeah, x equals 0, is that a legitimate solution? No, if we're talking about side lengths of a triangle, a side length of 0 makes no sense at all, right? That's not a triangle anymore. So we would discard the 0 and keep the 30, and we could use that 30 to plug back in to our other sides to figure out what they are, right? And that would give us, if we do all that, we get what? Plug them in. If x equals 30, then x plus 10 is 40. So there's one side length. 2x minus 10 is 50. So we get a 30, 40, 50 triangle. Okay? And that would work. Okay. What are they? What is all this 302? Are you getting, what's the 302, 402?
GCF time.
I'm not even sure what that, I don't know. I don't even know what they're doing here. Do you guys know what they're doing there?
That's checking the answer. They're just, I'm pretty sure. They're just checking.
302 plus 4 over 2?
I don't know.
Oh, is this supposed to be squared?
They meant
Trying to say
squared. It's supposed to be squared.
Oh, squared. There you go. Yeah, I got you. Okay. There we go. Gotcha. Okay, anyway, so we would check it out and it works. We're all good. Okay, last issue, and this is really minor. We've already talked about this stuff, but this is more of a review than anything. But what if we're just going to flip back to graphs of polynomials for a second? Solutions of a polynomial equation are the x-intercepts of the graph of the function, right? What do we know? Real zeros always correspond to, or real solutions in our case, to an equation, always correspond to x-intercepts. How come? Because when we solve this equation, when we solve polynomial equations, we're setting the polynomial equal to 0. So it's always going to be in standard form. And so when we go back and look at any one of these solutions that we want to, like if we go back to this page here, just as an example. So let's go back one more. So we end up with this place right here, this step where we've put the polynomial equation in standard form. So whatever is on the left side then, we're finding solutions of this polynomial that make it equal to 0, right? That's what a 0 means. Zeros of a function are the values of the function that make it equal 0. Okay? Well, the real zeros always correspond to x-intercepts. If I were to graph this function, it would cross the x-axis at 0 and -4, guaranteed. Right? Because those are the places where this polynomial that's on the left side is equal to 0. Okay? So if all the real solutions or the real zeros correspond to x-intercepts, then we ought to be able to pretty easily match these graphs up, right? Because if this is my polynomial function, this thing is going to equal 0. Where? At -3, +3, or so I could just look for the polynomial that has those zeros, and that's my answer. Furthermore, we also know that if we were to expand this out, we can do the leading term test also. What would the leading term be if I expanded this whole thing out? If I were to distribute that whole thing out, what's my first term going to be? X cubed, right? Everybody agree? Because when I FOIL this part out, I'm going to get an x squared. When I distribute the x, I'm just going to get x cubed plus a bunch of stuff. So from our leading term test that we talked about weeks ago, what's that end behavior going to look like? What's that one going to be? Show me with your arms. How would you classify that? Positive, odd. Yeah, so it's this one, right? So we also know what the end behavior is. So right there, that's a pretty powerful tool. We know end behavior, we know zeros. Man, that's pretty easy to identify a function then, right? So that one's got to be, well, I guess these both have the same end behavior, but which zeros are going to match, A, B, or C? B, yeah. -3, 0, +3. So that's A. First one is A. What about the next one? Yeah, so that's got 3 zeros, -3, +3, +1. It's got to be C, right? And then finally, this guy's only got 2 zeros, -3 and +1. So that's obviously A. Okay, make sense? All right. Okay, we're good. So we're done. I'm going to put up this assignment, and you guys now at this point, you've just got, I'm putting up reviews, I'm putting up practice tests, and I'm just going to give you a little time in class here this week to just work through stuff, right? At the end of the week, we'll probably do a little, I don't know if we need to do, you guys can decide if we want to do an in-class review or not at the end of the week. We can, okay?